All right. So we're going to be looking today at how to do each of the steps for bond energy, bond polarity, and molecular polarity. So I've got an example here. We've got O2 plus S gives SO2. So this is oxygen plus sulfur is giving us sulfur dioxide. So we've got to do these four things. We've got to find out the bond polarity, the shape of our molecule, the molecular polarity, and then the bond energy. So let's start off with the bond polarity. What we're doing here is we're comparing the electronegativity of this atom and this atom to see if there's a difference between them. And if that difference is significant, one of these atoms will pull more strongly on the electrons and we'll end up with a polarity. Polarity just means that your electrons are hanging out on one end of the molecule more than the other, or one end of the bond more than the other. So what we do is we have a look at our table. Electronegativity is the table we're going to look at to start with. And we're going to come over here and we find oxygen. Here's our oxygen. Oxygen has an electronegativity of 3.5. Now, in this particular molecule, both of our atoms are oxygen, so it's going to be 3.5 minus 3.5. 3.5 minus 3.5 is going to be 0. So the energy of this one, the difference between the electronegativities is 0. So we take that information down here, and we look at our chart. If we're between 0 and 0.3, we have a non-polar covalent bond, basically meaning that each atom is sharing these electrons pretty evenly. If it's between 0.4 and 1.6, it's a polar covalent bond, which means that they're still sharing the electrons, they're just not sharing them as evenly as you would expect. And then if it's above 1.7 to 4.0, then it's an ionic bond. There's no sharing happening here. One of the atoms has stolen the electron, the other one has given up on it entirely. So if we've got a 0.0, we're going to fall into the non-polar covalent. So we're going to write down for our bond polarity, non-polar. Non-polar. Great, so that's our first step done. Next thing we're going to do is look at the shape of our molecule. Okay, just going to switch colors here. There's a couple of things we need to do to figure out the shape. We need to look at how many atoms are attached to our central atom. We've only got 2 atoms here, so we're going to have to randomly assign who's going to be central. It doesn't matter. I'm just going to say this one is central. That's my central atom. So now I'm going to count the number of atoms that are attached. There is 1 atom attached. And I'm also going to count the number of electrons on my central atom that aren't paired to something. So there are 1 pair, 2 pairs. So I'm going to write 2 pairs. So I've got 1 atom attached and 2 pairs. Great. Let's go back to my chart. The first thing in the chart is the number of atoms bonded. We have 1 atom bonded, so it's going to be either this one or it's going to be this one. There's 1 atom attached. Now I'm looking for the unshared pairs. There were 2 unshared pairs. So it's not going to be this one because that one says 3. This one says 1 to 3, so it's going to be this one. Then we can look at what the shape is. Okay, the shape is going to be linear. So we just write down, okay, this is going to be linear. Great. So we've done step number 2. Next, we're going to look at molecular polarity. We're going to use this chart where we looked at the shape of it. We found out that it's linear. And then we scroll across and see the molecular polarity. Molecular polarity. And linear, most of the time, they're going to be non-polar. But it does say double check. So what do we need to do this double check? We think it's non-polar, but we have to check and make sure that it is actually non-polar. All right, so what is it we're checking? What we're checking is to see if there's any difference between the two ends of our molecule. So is this end and this end different? Well, in this particular molecule, they're not different. They're the same as each other. Because they're the same, there's no difference. There's no polarity between them. Because they're not different, we're going to say that this is non-polar. When we're doing these, we have to look at the atoms that are on the outside. So, for example, if I scooch over here to my other molecule, I'm not comparing this one and this one together. I'm comparing the ones that are on the outside. So I would compare this one and this one if I need to see if these two are different. You don't check the ones in the middle, you just check what's on the outside. We'll get to this one in just a second, but let's finish up on our first molecule. All right, so we know that these are not different, so that it's going to be non-polar. Great. The last step we need to do is the bond energy. So here is the bond. It's a bond between two oxygens, and it's a double bond between two oxygens. So what I'm going to do is I'm going to go down to my page that says bond energies. And I'm going to look for where oxygen is. So that's hydrogen in the first column. It's carbon in the second one. Silicon, germanium, tin, lead, not that one. Nitrogen, phosphorus, arsenic, antimony, not that one. Boron, not that one. Oh, look, here it is. Oxygen, sulfur, and selenium. So oxygen with a double bond, just like it is in my diagram, is 495. So I'm going to put down 495. 495 kilojoules of energy is required. Now, this is a positive amount of energy. Anything that is on the left-hand side requires me to add energy in to break these bonds. So anything on the left-hand side is going to be a positive energy amount. On the right-hand side, all of this stuff is going to be negative. This is energy I get out. This is exiting. This is entering. Anything on the left is positive, anything on the right is negative. Okay, so we finished up that one. Great. Let's look at our second component in this reaction. We've got S. S is an atom by itself. So there's not going to be any, there's no bonding happening here. So we can just put a dash through bonding. There's no shape here either because we've not got a molecule that we're connecting together, so there's no shape. There's no molecule to describe here, so there's no molecular polarity. And there's no bonds, so we have nothing to calculate here. All of this is blanks. Okay, you don't need to do any of the work on this because it's not bonded to anything. There's no bonds, there's no energy, it's just an atom sitting out there by itself. So that makes that pretty easy. So now we can figure out the total amount of energy in. Well, this one was 495, this one is effectively 0, So my total energy in is going to be, I have to apply 495 kilojoules of energy needs to go into my system. Let's jump over here to our last one, sulfur dioxide. Bond polarity, so that's where we've got to start again. So I think that was green for consistency, yes. Scroll up and we're going to start off by looking at so this time we have sulfur and we have oxygen together. So I have to find the difference between these. Oxygen is 3.5, sulfur is 2.5. The difference here is a 1.0. That's the difference between those two. So oxygen's clearly pulling harder on this than the sulfur is. How much harder? Let's see if it's going to fall in the polar covalent or non-polar covalent. Non-polar covalent is 0.0 to 0.3, so it's not that one. It's going to fall right here in the middle between 0.4 and 1.6. So it's going to be a polar covalent bond. So on my right-hand side, I'm going to write down that this is polar. The bond type here is polar. Awesome, off to a great start. All right, now we need to look at what the shape of this molecule is. Here is our central atom. We don't get to pick this time because there's one in the middle. So I have to count the atoms that are attached. There's 2 atoms attached, so 2 atoms. And then I count the electrons that aren't being used. 2 unshared pairs. All right, so now we go back to our reference table. Clean that up just a little bit. Okay, so this time we have 2 atoms attached, so it could be this one, it could be this one, it could be this one. Number of unshared electron pairs, it's not 0, it's not 1, it's 2. So our molecule is going to be bent in shape. So we just come down here and we write bent. So our shape is bent. Now we look at molecular polarity. Here's our molecular polarity. And we're in this row, and it says that it is polar. And it doesn't say double check, it just says it's polar. So we don't have to do any more work. If it is bent, it is going to be a polar molecule. So I just write down polar. All right, last thing we need to do is find the bond energies. So I'm going to clean this up just a little bit, get this stuff out of the way, just so we can see what we're doing. All right, so I need to look and see what bonds are being made here. Well, there's bonds here and there's bond here. This is an O double bonded S bond, and the one on the right is the same thing. It's O double bonded S. So I need to find O and S double bonded together on my reference page. So I'm going to open up my reference all the way down here to bond energies. Okay, here we go. It's listed the other way, SO, but that doesn't make a difference. It's 522. So the energy I'm going to get here is 522 kilojoules. And the energy for this one is 522 kilojoules. Now, we are on the right-hand side of the equation this time. I'm not breaking bonds, I'm making bonds. And when I make bonds, I actually get some energy out. So these two are going to be negatives. This is negative 522, negative 522. So my total is going to be negative 1,044 kilojoules of energy. That's the total amount of energy. Negative 1,044 kilojoules. All right. So we're almost done. We're almost completely finished with this. The total amount of energy we put in was 495. Let's have a look at the total energy we get out. Well, there's only one molecule being formed here, so I don't have to do any calculations, but I'm just going to put it in my big box here. It says energy out is negative 1,044 kilojoules. So now if I want to find the total energy for my system here, it's going to be 495 kilojoules minus 1,044 kilojoules. I'm going to throw that in my calculator. 495 minus 1,044 equals negative 549 kilojoules. Now, let's remember that let's say entering energy is endo for enter and thermic for energy. Exiting energy is exo for exiting and thermic for energy. So, do we have more energy going in or more energy coming out? Well, because this is a negative, we have energy exiting. It is leaving our system. So this is going to be an exothermic reaction. Energy has exited my system here. So I hope you found that helpful. This is what the expectation is for the test. It's a lot of steps. It's a lot of just jumping through points along the graphs and finding all this information. If you are having trouble finding something on this reference sheet, ask, okay? I want you to be able to, if you know what you're looking for and you just can't find it, or it's taking you a long time to find it, ask the question and I can point you in the right direction, okay? I hope this was helpful for you. I hope you have a wonderful day.